Dear students, through this video, we'll learn principles of mathematical induction. To prove any statement P of n is true for all natural numbers, we must go for two steps. The step one is, we must prove P of 1 is true. That is, the P of n is true for the initial value. And step 2 is, by assuming P of k is true, we must go for P of k plus 1 is also true. If we are proving these two steps, we can conclude our statement P of n is true for all natural numbers. Note that we are having a two step and the two steps having a name. The step 1 also called a basic step and the step 2 is also called an inductive step. Now we'll prove the following problem using mathematical induction. Consider the problem 1. The problem 1 is, for all n greater than or equal to 1, prove that 1 square plus 2 square plus 3 square plus 4 square etc. n square plus n square is equal to n into n plus 1 into 2n plus 1 divided by 6. Actually, this is a formula of a sum of squares of n natural numbers. We studied this one in our 10th standard level itself. And now I want to prove this one with the help of a mathematical induction. I am denoting let P of n is equal to 1 square plus 2 square plus 3 square plus etc. n square is equal to n into n plus 1 into 2n plus 1 divided by 6. First, I want to prove the basic step 1. That is, I want to show P of 1 is true. So, I will check whether the P of 1 is true because the n value is starting from n greater than or equal to 1. If you are considering P of 1, the statement becomes 1 square. Okay, we have to stop up to 1. That is, I want to give n value is 1. Therefore, I am getting 1 square. 1 square can be written in the form of this is equal to. I want to check whether it is true or not. I am putting n is equal to 1. Then you are getting 1 into 1 plus 1 into 2n. N is 1, I think. N 2 into 1 plus 1 whole divided by 6. So, this is equal to 1 into, this is 2, 1 plus 1. That is, you are getting 3 divided by 6. Exactly, you are having it is equal to 1. That is, I am getting the left hand side is 1 and right hand side is also 1. So, therefore, you can conclude P of 1 is true. P of 1 is true. Now, I want to go for the inductive step. The inductive step is, this is in step 2. I want to assume P of k, actually the P of k is, that is 1 square plus 2 square plus 3 square plus etc. plus k square is equal to k into k plus 1 into 2k plus 1 divided by 6. It is true. I want to assume like that is true. This must be the inductive step. Now, I want to conclude the inductive step. I will go for P of k plus 1. That is, to prove P of k plus 1 is true. For that, I will start with the P of k plus 1 left hand side. Actually, the P of k plus 1 having a statement 1 square plus 2 square plus 3 square plus etc. plus k plus 1 square. K plus 1 square is equal to, actually I want to prove this one is equal to k plus 1. That is, it is looking like n into, actually in our problem it is given as n into n plus 1 plus into 2n plus 1 divided by 6. So, in that form, if you are writing k plus 1 means you are getting k plus 1 into k plus 1 plus 1 into 2 into k plus 1 plus 1 whole divided by 6. If I am proving like that means the problem is over. Now I am checking whether it is possible to prove this one or not. This statement can be written in the form of 1 square plus 2 square plus 3 square plus etc. plus k plus 1 is there, but the before term you are getting k, therefore I am getting k square plus k plus 1 square. I just remodify that one. Already we assumed earlier, our statement is true for P of k. That means you may write this statement as k into k plus 1 into 2k plus 1 divided by 6. That I am doing now. Therefore, I can write this term as k into k plus 1 into 2k plus 1 whole divided by 6. I may write like that, and the remaining will have k plus 1 whole square. Now I am taking a LCM of this one. I am getting k into k plus 1 to k plus 1 plus 6 into k plus 1 whole square whole divided by 6. Then next I will take the common thing out. You have common thing is k plus 1. I will take out the common thing k plus 1. Then the remaining is k. Here the k plus 1 is taken out, and from this I want to reduce one more power. Therefore, you are getting k into 2k plus 1 plus 6 into k plus 1. That's you are getting whole divided by 6. It is equal to k plus 1. I want to simplify this one now. I am multiplying inside. If you are multiplying, you are getting 2k square plus k plus 6k plus 6. I am getting like this whole divided by 6. This is equal to k plus 1 into, I am simplifying this one. I am getting 2k square plus 6k plus this one is, I am getting 7k plus 6 whole divided by 6. This is equal to, I am planning to factorize this one. From this, I am getting k plus 1 into, I can write this 7k in the form of 4k plus 3k plus 6. This is this modification to factorize the corresponding term divided by 6. It is equal to k plus 1 into, from that I can take a 2k out. So then you are getting k plus 2 is the remaining, and plus, and from that you can take 3 outside. Then you are having k plus 2 is the remaining whole divided by 6. It can be written in the form of k plus 1 into, the both having a common k minus k plus 2 should be taken out. What is the remaining you are having means 2k plus 3 whole divided by 6. Finally, you got the conclusion. It can be written in the form of k plus 1 into k plus 1 plus 1. I am modifying here to k plus 2 plus 1 whole divided by 6. This gives the idea. It is equal to k plus 1 into k plus 1 plus 1 into 2 into k plus 1 plus 1 whole divided by 6. Yes, which is a recurring thing, and we concluded our 1 square plus 2 square plus 3 square plus etc. plus k plus 1 square can be written in the form of k plus 1 into k plus 1 plus 1 into 2 into k plus 1 plus 1 divided by 6. Therefore, k plus 1 is true. Therefore, we can conclude our statement P of n is true for all integer n greater than or equal to 1. This is by the mathematical induction. I just recollect what we did earlier. Look at that. I want to prove the statement, and I will consider as P of n by the induction principle. Basic step is how to prove. The basic step is proved for 1, and we concluded P of 1 is true. For the inductive step, we have to assume P of k is true. So then I assumed up to k the term, and I want to show P of k plus 1 is true. For that I am considering P of k plus 1, and I concluded with the help of the mathematical calculation, and this is a conclusion you got. Finally, we arrive that the P of n is true for all the integer n greater than or equal to 1. Thank you, students.